Cool. I think we're roughly at time. Maybe I'll give it another minute for any late stragglers. How's everyone doing? I know this is the last session, right? But before, oh, and there's one like awards thing for like 10 minutes, right? And then the party, right? Yeah. So, I'll just go ahead and get started. I don't want to keep you. So yeah, I'm going to talk about basically small language models, like how to fine tune, and more importantly, like quantizing small language models and using them in agentic AI solutions. And there's actually, like kind of talking a second ago here, like all of the demos that you see, there is a GitHub repo, which will be at the end in my resources slide, that actually has the code and everything. And if you don't want to burn your own money training these models, I actually also have the models downloadable so that you can just download them and exercise them on your own too. So let's go ahead and just jump into it, right? So my name's David vonThenen. I'm an AI ML engineer at NetApp. I've been doing AI for before ChatGPT, before it became cool and announced. And I like to do everything from like AI on edge, vision-related models, and even building like ML models to detect disease. So I actually have trained a machine learning model to detect Parkinson's disease, which is through speech and also through like walking too, so through gait patterns. And prior to that, I was in the Kubernetes ecosystem, so a lot of systems engineering. I have a huge background in storage, so doing backup recovery solutions for virtualized environments like VMware vSphere, so like stuff like that. So I thought it kind of set the scene here, and like let's talk about some unsettling things in AI and like what's happening in the AI space as it relates to economics. And that's kind of going to be like how to like look at the talk and understand like why you should care about small language models. And so we're going to talk about small language models. We're going to then talk about fine tuning and quantizing. And so this is the ability of like imparting knowledge on small language models, and then also then reducing the size of these models so that you can run them even on like laptops, whether they have acceleration or not. And then we're going to use those small language models in an agentic solution. So no hand waviness, like an actual 2 agents with an orchestrating agent, so multi-agent demo that'll actually hopefully work. We'll see. And then we'll have some Q&A at the end. So let's talk about some unsettling things that have been happening in the AI space, especially actually very recently. So who's heard of OpenClaw? At this point, I'm pretty sure everyone has, right? So it's the fastest growing project in history. When I created these slides, it had 350,000 GitHub stars, which has far surpassed even the Linux operating system, which is just to go show you how much this is growing and how much these autonomous agents are quote unquote going to change our lives, right? Now, even though that was the cool, trendy thing to talk about, that wasn't, for me, that wasn't the news story that people should be paying attention to. In fact, I think this is one of them. The first one was the security problems that it had, but I think this one is the actual story that people should be paying attention to. And this is basically a news clipping of someone posting on Reddit that basically said that they ran OpenClaw for 12 hours and their bill was $2,200 US, which is a ton of money for 12 hours. I really hope they got their money's worth out of that $2,200. I somehow think they probably didn't. And so, running these agentic systems on, let them loose and let them go and sit there and think about and burn tokens, it's a real money burner. And I think that might foreshadow some of the stuff that we're going to talk about today. You probably also heard this too, right? This was around NVIDIA GTC. Jensen Huang basically said, if your top AI engineers aren't burning $250,000 in tokens a year, then there's something wrong. And I think this might foreshadow some of the stuff that might be happening, especially towards the end of this year and like the beginning of next year. And then there's also this other cool news clipping where it's a tweet that went out. So Uber gave their engineers, so 5,000 engineers, they gave them a budget to use AI tooling in their everyday workflows, right, to build Uber-related products. And they burned through their entire year's worth of AI budget by April. And I'm sure that it was probably in the tune of millions and millions of dollars for 5,000 engineers. But that's quite an unsettling number, right? That the amount of money that's being burned, like running these AI systems. And here you see this other thing, right? This other news story where it's basically NVIDIA did a acqui-hire / non-exclusive agreement to purchase Grok. So basically be able to use their hardware. And if you're not familiar with what Grok does, they're actually an inference platform. But more importantly, the inference platform that they provide you to the public, the end user, they create and build their own hardware. And actually the co-founder or the founder of that company actually worked at Google building their TPUs. And now you have NVIDIA coming around saying, hey, we want to purchase a licensing agreement plus an acqui-hire for your TPUs at Grok. And so this is kind of what we're going to talk about today and how we're going to kind of frame it from a financial perspective. So let's kind of keep that in the back of our heads, and then let's go ahead and talk about small language models. So what is a small language model? Has anyone heard about small language models? Everyone sure definitely have heard about large language models. So what are small language models? So they're the exact same thing as large language models, except they're significantly reduced. So they do the same thing. You provide an input, they process, they understand the context of what you're saying, and then they generate some sort of natural language response, right, your answer. So they do exactly the same thing. The big difference is that they're much smaller in size, right? Instead of like hundreds of billions of parameters or now even trillions of parameters, which, right, GPT 5.5 was released today. So, you're starting to get into trillions of parameters, but small language models are kind of anywhere from hundreds of millions of parameters to like roughly 10 billion parameters. So significantly smaller in size. So anywhere from like 50 to 100x smaller, right? And instead of like large language models that can do everything, like from, if you ask it about turtles, it'll cool. If you tell me, like ask it a large language model how to bake a cake, it'll totally understand. If you ask it for legal advice, large language models are cool for that. But small language models, they're purpose built and for very, very specific things. And typically the only thing that they're usually good at is one thing, and it's usually language related. And the reduction of the number of parameters that these small language models, like why you do that is that it's much cheaper to run these models versus, these 100 billion type parameter models, these large language models, right? And so by doing that, you can actually use like lower end GPUs, or even on like my MacBook here, I'm going to end up using the MLX, so the Apple Neural chip. Or you can even run them on CPU and they'll perform actually just fine. So kind of like the goal is cheaper, faster inference, and then if it doesn't know a particular domain, you take that small language model and you teach it that thing, right? And so that's kind of like what a small language model is in a nutshell. And then this is just kind of a good slide to do a comparison, right? Like a small language model versus a large language model, right? Large language models, super advanced reasoning, they know everything because they've been trained on the world's data. They can do it all. And small language models are very purpose specific, built for one thing. Typically they only know language like English, Spanish, and if you want to, and most of the time that's actually good enough, believe it or not, like especially if you're only doing language related processing. Believe it or not, these small language models can do a ton of things, like summarization is a pretty decent one, providing that you give it like a document to summarize, right? But there's a difference, right? Large language models do it all. Small language models are very focused. That's kind of like the takeaway. So that's good and all, But what about like the economics? So if we take two sets of problems, so we look at very highly complex problems, and we compare like what a small language model and a large language model look like when you run inference and like what the cost factor is. So running those two different models from a cost point of view is basically, for like high complexity reasoning type things, is 94x, 94 times the cost of a small language model. So large language models cost a whole lot more to run, right? Because the hardware, GPUs, cooling, power, water, all of those things. And when you're taking a low complexity task, so something that's much easier like summarization, for example, and you compare, and that's the bottom one right there, if you compare like the difference in cost to run those models, you're looking at like roughly 100x difference. So depending on your workload, you're looking at a 100 or 94, 95x to a 100x cost difference in running models. And the person who ran OpenClaw for 12 hours, that's the cost of hitting those large language models, right? Using like Opus, I think it was Opus 3.7, like the maximum Anthropic model, right? So if you think about what requests typically go to large language models, they fall in 3 buckets. And the frequency at which they fall into these 3 buckets are like literally right here. Believe it or not, roughly 80% of the prompts that questions that people have for large language models, or language models in general now, fall into I can actually use a small language model to process this request. And then 15% of them might require that advanced reasoning. So it's a very complex problem. I'm going to feed it to a large language model because it requires that extra reasoning, like the larger context window and all that great stuff. And 5% of the problem might roughly require like human intervention, right? To refine the prompt, to refine like if you've ever used a deep research prompt and you say, hey, I want you to go research that, before it just goes and does it, have you noticed that it actually says, this is the plan that I'm planning on executing, and you have the option to edit that. And the reason why is so you can fine tune it, excuse the pun, to make it research better, quicker, faster, get to the point even quicker. So that's that human expert portion. But if you just look at this graph here, you can have a massive savings just routing the request to the right model. And this is the reason why you're starting to see things like OpenRouter hit the market. You don't send all of your requests to, Claude Opus 3.7, the maximum, right? Because it's the most expensive. You can actually redirect 80% of them to lower cost models that can perfectly answer those types of questions, and then reserve just 15% to those models that are truly very expensive. And so like that's literally what the definition of that OpenRouter service is, right? It's picking which model to run the problem, to best run the problem, to reduce your costs on how much it costs for inference. And if you're still not convinced, this is a research paper from NVIDIA. Small language models are the future of agentic AI. Now, why is this important? It's important for 2 reasons. The first is NVIDIA, their entire bread and butter, how much money they make, they would make more money if you just wasted your tokens, right? Because they need to buy more GPUs and, they'd get more money, their revenue would go even higher, right? Waste is good for them because it requires more hardware. But from a credibility standpoint, they can't go up there and say, hey, like, just run large language models. No, because they also understand the cost of inference and how much waste in power, energy, cooling, that all kind of will start to accumulate and snowball into when we get into this agentic world where we have multiple agents, multiple LLMs running in our data centers. And so even from a pure credibility standpoint, this is the paper that they have. And so we're going to kind of dive into this a little bit in the next section here. So if they're saying, so we're going to talk about fine-tuning and quantization. First, what it is, what they both are, and how we apply them to small language models. And so if we're going to try to use small language models more frequently to reduce our costs for running our agentic systems, we have to have, one, the ability to target the actual hardware that it runs. Believe it or not, they run on computers. And two, we actually need, if we need to teach them things, we have to have a mechanism to update their knowledge base, right? And so that's exactly what fine-tuning is. So fine-tuning is taking an existing model that's already been pre-trained, which is a typical small language model, right? And the ones that I'm going to use in all of the demos for the two agents that I've created. How many here has heard about Qwen 2.5? Okay, few AI people here in the room. Okay, so it's a small language model, 7 billion parameters. And what I'm going to do is I'm going to impart specific knowledge onto these pre-built models to do and give them the knowledge to do things that they haven't been trained to do. And so this is how you start to specialize these agents to do things specific, purpose-built, right? Be a subject matter expert. And so how you fine-tune is basically the same way that you'd train like a machine learning model. Is you provide it data, you have a training process, you do an evaluation, and then you make sure that the model that you've trained, fine-tuned, can answer those types of questions. And so for like the non-technical folks who aren't in like the ML world, so think about taking like an existing project on GitHub, forking the project, and then making a feature branch that drastically changes the project to only do one very specific thing. And that's exactly what fine-tuning does, right? You're taking an agent, adding some knowledge to it, and making it only do one specific thing, right? Be a subject matter expert. Yeah, I'm going to go ahead and skip this. There are actually, I'll talk about it real quick. There are actually cases where you want to fine-tune models and do RAG. That sounds very weird. And the reason why you might want to do that is if you have a great example is if you're trying to create a medical model, like medical language, large language or small language model, that small language model probably doesn't have the vocabulary to understand medical related terms and concepts. And so that's why you might need to fine tune that particular model so that it understands like penicillin is, a drug, right? And you also might need to use RAG to provide that newly fine-tuned model additional data that is newer and relevant to like what's happening today. So that's why you might want to do both. So if we have created this subject matter expert, and we're going to create 2 of them today, and where I'm going to demo them live. Obviously, we can't train them because that takes far too long, but if we have these 2 subject matter experts, we want to be able to target them to run on specific hardware. And the reason why we might want to do this is that it makes the math a lot easier for these models to run on my laptop, for example. So most models, when you train them, they use floating point 32. And what you want to do is you want to quantize them or change the math problem so that instead of using floating point 32-bit numbers, you use something like integer 8-bit numbers. And by changing the math problem on these language models, you can actually have a massive savings on the amount of hardware required and cooling and all that other stuff. And believe it or not, the inference is actually a lot faster because you're now targeting a specific hardware platform and you're removing things like what is a turtle or a unicorn out of that language model when it doesn't need to know about that stuff, right? And by doing that, you have the ability to run on CPU, or in my case, I'm going to use the Apple neural chip on here. So it's like, the M1, M2, M3. I have an M1, so it's the lowest end on purpose. But yeah, so that's what quantization does. All it does is just change the math problem. And yes, you might take a small hit in how you might take like a small hit in the knowledge of the agent, but I would argue that when you fine tune, you're purposely adding the most relevant stuff back into that agent. And so when you quantize, you're effectively getting a lot better performance because you're only building this small language model to do one very specific thing. So kind of this is like a before and after snapshot, like kind of the upshot of it is when you quantize a model, the memory footprint is much lower, right? And if you think about it, floating point 32 is like what you normally train a model on. So that's 32 bits, but if you quantize to 8 bits, you actually have reduced the thing by 1/4, right? The amount of memory that it needs to load the model, just because you've changed the number of bits that this model now has to do the math problem on, right? And because of that, the math is easier, which means the inference speed is faster. The correctness, like I said, takes a small hit, but I actually wouldn't worry about that because the fine tuning kind of fixes that. So believe it or not, when you quantize, you actually want to quantize even if you are running a GPU. And that might sound crazy and it might sound weird, but the reason why you do is because the NVIDIA GPUs prefer a specific math problem, a math format. And that math format is BF16, which is different than FP or floating point 16. So you actually do want to quantize the models that you create. Now, will the models run unquantized just fine on an NVIDIA GPU? 100%, and it's because those things are massively expensive, right? 40, 50, 60, $100,000 GPUs, right? But if you quantize them into their preferred format, you'll get like I think it's like a 3 to 5x faster inference rate than if you didn't. And so you should definitely be aware of that. And you can also quantize to run on commodity hardware, like my laptop here, which is, there's other CPUs that have extensions on them, like the Intel chip has the AMX extensions, which basically help with floating point calculations and that kind of thing. And my MacBook on the Apple Silicon has accelerators, like the neural engine, to help do the math for language models on my laptop. So instead of just talking about it, which I'm sure boring the heck out of everyone, I'm going to do 2 demos. We're going to create 2 different subject matter experts. One is a subject matter expert that understands SQL. I can ask it SQL questions. I can ask it to create SQL statements. Tell me about SQL. It'll help. So that's one we're going to train. The second one is a Python coder. So this thing can actually understand how to code Python. Again, using small language models that will run on my laptop here. So you can see I used Qwen 2.5 7 billion parameter model to start. I used these 2 data sets, a SQL data set and a Python data set, to impart the knowledge on each one of these 2 agents. And I quantized them down to int4 so that I can run it on my laptop. And yeah, let's go ahead and take a look. So for the Python one, I'm just going to run the inference on it really quick. So by the way, this code, again, it'll be at the resources page at the end of my slides. The code to train, quantize, and run inference is all of the code for all the demos here are on there. So you can go home afterwards and do this yourself. And if you don't want to burn money training the models, like I said, there's models you can download that I've trained already that you can just download and run yourself. So to train, you would do, or to fine tune, right? We're taking that Qwen model and imparting Python knowledge. You would just run this script. It'll automatically download the data set, do the fine tuning. You need like an H200, which is why it gets expensive. And this will fine tune the model. We're not going to do that because it takes like 10 hours. Then to quantize, depending on the type of hardware you want to hit, I have an Apple, so I'm going to use the MLX script here. And if you don't have an Apple laptop, you can target CPU. And that'll take that fine-tuned model. It'll reduce it down to make the math easier so that I can run inference. And let's just go ahead and do that. So we're going to give it a question, a Python question, that basically says, hey, I want you to slugify, which is, when you look at a URL and you like publish a blog post, you can't have funny special characters in that URL, right? So a slug is that, like normalized URL. And so in the time it took me to explain what slugify means, it's actually already finished, right? So it says, the question is write a Python function to slugify. That means lowercase, white space, remove white spaces, remove alphanumerics and that. And this is the answer. So you literally saw this in real time. And not only did it provide you the function, but it provided an explanation, and it also provided code to actually run the function. And it did it in a total of 11 seconds, right? Much cheaper than having all the hardware, the cooling, and all that stuff, right? So that's Python. So let's go ahead and look at SQL. Again, the same thing. To fine-tune the Quen model so that it understands SQL, run python1_fine-tune. To quantize it, again, you can either target Apple, which is the MLX stuff, or you can do CPU, and that takes some time. So we're just going to run inference, because I'm on my Apple here, MacBook. We're just going to run the MLX.py, and we're going to ask it a Python or a SQL question, which is going to ask, based on this table here, I want you, which is a table of employees and departments, list the first and last name of all employees who work in the engineering department. And you can see that that is absolutely correct, right? It's nested a select statement in there to get the department ID, select first name and last name from employees where department ID equals that. It took 1.9 seconds on my laptop here, right? So pretty cool, right? It's pretty powerful. Like I can actually run these models. Now, had that person who was running OpenClaw run their model that's quantized for their laptop, probably would have saved themselves $2,200. So it's, and by the way, that demo was recorded and they have YouTube links so you can actually watch the thing at home. So let's talk about these small language models, but with agentic AI. So like OpenClaw and like, OpenClaw and Claude Code and all that stuff, those are all agentic systems that require, that they have very specific things, right? They reason on their own. They kind of, when they're given a problem, they decide what the plan is to like answer that particular question. They define what each task is. They execute for each task, and they have memory so that they can make sure that they don't redo one of the tasks, right? That would be stupid if it was stuck on a loop doing the same task over and over again. So we need to know what we've done before and all the parts so we can aggregate that information to answer the question. And they also define what done looks like, right? And so in practice, what an agentic system is agents, usually composed of large language or small language models or large language models, a language model. There's state, there's some form of memory, there's an agentic loop, and there are actually many different types of loops. They go through a period of like refining the answer in some fashion. They decide when to stop, when they've got the answer, and they can access tooling. And that's literally just what agentic AI is, right? That's it. Don't want to demystify that. It's not some craziness or anything, right? So here are a list. I can't cover all of them because this is actually this is the first time I'm giving this talk. But I had built this for another session next week at Open Data Science Conference. It's supposed to be an hour long. But here's a list of all of the different agentic loops that you can do. And we're only going to look at the last one, which is the multi-agent one. And each one of these loops does something very specific. It has a specific architecture and how it answers a problem. And we're going to take a look at a multi-agent system. So a multi-agent agentic system is literally this. You have multiple agents that can all talk to each other. And at the top here, you can see the agent number 1. There's usually an orchestrating agent, an agent that basically handles the communication of like what still needs to be done, who needs to answer this question, how I hand off the answer, the question off to that thing, get an answer back, then use the collective answers in order to answer a problem. So that's what the orchestrator agentic pattern looks like. And that's also going to be what we're going to demo here in a second. Now, there are many different frameworks, SDKs, and all that stuff, whether they're tied to cloud that's paid or different frameworks that you can run on your laptop. There's OpenAI has their agents SDK, so does Claude. There's, Crew AI. We're actually going to use just bare bones agent-to-agent protocol because I like building stuff on my laptop. I don't like if I can prevent giving even more money to some of these corporations, I'm going to try to choose that route first. So we're going to use agent-to-agent protocol because it's open source and it's free, right? And what agent-to-agent protocol is it allows you to have agents communicate to each other. It's literally just a protocol definition. And it supports different transport mechanisms, so like HTTPS, JSON RPC, and I believe gRPC is almost on its way. Like I think it'll probably be maybe another month if it's not already there today. So there's different communication transport methods, but it just allows, it's a protocol, like a contract on how agents can talk to each other. It's open source, so it was initially developed by Google. And that project was donated to the Linux Foundation so that, there's, fair for everyone, no one vendor controls anything. And kind of the idea is that you use that multi-agent architecture, that orchestration architecture, and you have a collection of subject matter experts where you divvy things out. You divide the work out, and you have this one orchestrator agent that kind of like keeps the eye on things of like who needs to work on what and like what answers I need in order to get to an answer to the user. So for our demo, this is what we're going to use. This is what we're actually I'm going to run this right now. We're going to use agent-to-agent protocol to allow that same Python agent that I demoed a second ago, that same SQL agent that I demoed a second ago, and we're adding that orchestrating agent here. And the orchestrating agent that I'm using, it's another small language model called Nemotron. It's developed by NVIDIA, but it's called Nemotron Orchestrator. And so when we query our orchestrator, the client queries the orchestrator. It says, this is the problem I want you to work through, and it then kind of goes from there. And we'll actually see all of its thinking stages too. So if you're not familiar with Nemotron Orchestrator, it's available on Hugging Face. It's just an orchestration model. So this sounds weird, but it's a small language model that's purpose-built. So its job and its only job is to orchestrate. And so compared to like other language models, whether they're large language models like OpenAI, you can actually see, if you've never heard of Humanity's Last Exam, it's basically a metric to see how well your model does in certain aspects of like whatever. And for orchestration, I know it's not number one, right? XAI is up there, OpenAI with GPT-5 Pro and Grok 4 or whatever, but it's number, 5 right there? But the difference is I can run this on my laptop and it doesn't cost me any money instead of having to hit OpenAI 5 for running an orchestrator model, right? And if you take a look at the cost and accuracy for the Humanity's Last Performance, you can actually see in the graph there, like, notice that the green line is much cheaper, and that's kind of the whole takeaway from all this, right? So let's go ahead and demo that. So, gonna run our Python agent. Again, I'm on my Apple, so this will provide all the Python expertise. We're gonna go ahead and run our SQL agent. This is going to provide us all of our SQL knowledge. Make sure that these are running. And then we're going to start that orchestrator agent. I'm just going to run in CLI mode. It actually does have an option to have a REST interface on there, but I'm just going to run the orchestrator in CLI mode. If you wanted to run it as a service, just go serve. So when you want to do this at home, I have an accompanying client that will talk to it, a REST client. But we're just going to run it in CLI mode, and we're going to give it a problem. And the problem we're going to give it is, I want you to write a Python application that can query a SQLite database to give me the highest paid employee at a company. And that's what we're going to have this agentic system work through. So you can see, like right here, right, it's thinking. So, okay, we need to write a Python application that can query a SQLite database. It actually kind of already understands right here that this is what the query might look like for SQL. But it says, I actually need to go and verify that, which is, I need to make sure it's correct. So this is reasoning in real time. And then it says, I need to make sure it's correct, so I'm going to consult the SQL agent. And it probably already did by this point. Nope, wrong window, right? This is, you can actually see this thinking its way through this, right? Select from employees where salary equals, get the maximum salaried employee. And then it says, okay, cool. Now that I have the SQL thing and I've confirmed that it's good, we obviously need to have a Python application to invoke this thing, right? And it's basically reasoning through all, so the orchestrator agent, which is the dump that you're seeing here, it's reasoning through how I complete the rest of this problem. And it says, I probably need to consult the Python agent. And so it's going to go ahead and, after it's chatting away for a lot here, call the Python agent with the SQL statement. And you can see that we're providing the SQL statement, the dialect is SQL 3, and we're going to go ahead and it's going to create a Python application for us using that SQL statement, and hopefully in a second it will output the answer. Import SQL 3 Lite, connect to the database, query, print the result, close the connection. Now, why is this cool? I have 3 models running on my laptop. I did not hit the internet. I'm not paying anyone to figure out this stuff. And that's the point of this session here. So remember the cost of everything, right? They're all saying that tokens are going to be the next oil. That's how much it's going to cost. And Jensen Huang, I don't think, is wrong. The tokens is only going to climb exponentially when these agentic systems start getting out there, like OpenClaw. You can already see that, remember, Anthropic cut off OpenClaw, so now that you have to hit their API. Before, people were using the pro account, and they cut that off. CapEx is rising. So last year, we were in like tens of billions of dollars per hyperscaler in 2025 CapEx. 2026, we're at multiple hundreds of billions of dollars in infrastructure. Where is the profit for them? Now, you have to figure at some point, they're going to crank this thing up so much, 100, 1,000x per token, because they have to recoup the cost in the hardware, the cooling, the data center spend, right? This was a test that Anthropic just did. Hey, we're gonna remove Claude Code from the Pro edition. And then everyone got all, right? And everyone screamed and they added it back, right? Now we have to ask ourselves, are we on a sustainable path with the cost of tokens, right? And if we're gonna replace the hardware, the GPUs, every 3 to 5 years, right? The H100s were super expensive, $40,000. The H200s was 2 or 3 times faster than the H100. Vera Rubin is going to be 2 or 3 times faster, already obsoleting the H200 architecture. It doesn't make sense to keep buying all this hardware. And again, don't take my word for it. That's the reason why NVIDIA is investing in Grok for their TPUs. That's the reason why Google looked at, their memory compressor for LLMs. They are investing in it. And my advice to you is, invest in small language models, fine-tuning and quantization before you get caught holding the bag of money, handing it to them. Resources. So everything you saw, all the code for everything is in that GitHub link right there. And I actually am going to be at Open Data Science Conference next week. There is a podcast that I did with the founder of Open Data Science Conference. I have the links for them, listen to them. I also have an accompanying blog post. And also, just for your information, you should think about KV cache. If you haven't heard of it, it's just a caching mechanism. But all it does is it hopefully caches so you don't have to hit expensive GPUs. And that is the session. Thank you. Did I go over or are we good on time? I think this is the last one anyway. Anywho, if you have any questions, I'll hang out here and I'll definitely be at the party. But yeah, thanks for listening. Hope you found it useful.